Do you want to learn how to improve your 3D print quality, consistency, and strength for free? Because that's what I'm going to show you how to do in this video. What's that? I can already hear somebody typing away in the comments.
Filament tuning? That's so old school. My printer tunes itself.
If you're not tuning the filament profiles, you're just using a generic profile, you are leaving improvements on the table. I'm aware that there are current gen machines that claim to auto-tune filament for you. However, at most they tune 1, maybe 2 of the 6+ variables we're about to discuss, and I personally find that a manually tuned profile is still superior. If you're happy with the auto-tuning functionality, by all means, stick with it. But I challenge you to give what I'm showing you at least a try and see if you can't find room for improvement. Timestamps are in the description if you want to jump to any specific tests. For the equipment we're going to use, it's going to be my 3D printer farm from Prusa Research, sponsor of this video. But we need filament to build a profile around. I've decided to go with this Ambrosia ASA for our testing today. First, we've got to get it out of the package the only proper way. This stuff prints pretty easy, but I did choose ASA so that we can have a slightly more challenging material, at least compared to a basic PLA. I picked this particularly striking color called Grape because I liked the way it looked. I hope it shows well on camera so you can really see the details we need to see. Before we get to tuning, we need to make sure this stuff is good and dry. If we don't, it'll throw off some of our results in the testing process. But wait, how do you know if filament is wet? Well, it won't be this obvious. The plastic absorbs the moisture, so it's inside of it. Really, printing with it is the best way to know. The first thing you may notice when loading filament is some steam coming out of the end of the nozzle, and then as it extrudes, you might notice some bubbles actually popping and forming as it exits the nozzle. That's the moisture baking out of the filament. If you don't notice that, you might go ahead and run a print and end up looking like this. Lots of stringing and blobbing. Ironically, this was meant to be a filament dry box to keep filament dry. Those are the most common symptoms, but I've also seen a weird one more than once where these materials that are listed as like metallics or shiny ABS or ASAs get a surface texture on it that's a little bit whitish discolored. It's weird, but it does happen. And yes, even fresh out of the bag, some filaments could stand to be dried. I don't feel that PLA needs to be dried nearly as much as the internet says, but there's a bunch of other materials that really benefit from it. And storing your filament in dry space is always great. Well, if only manufacturers gave you a way to do that out of the box. With the filament dry, we can load it up and start tuning. First up is temperature, because getting this wrong can throw off every test that comes after. Too hot can increase stringing and hurt cooling. Too cold can limit speed and reduce the layer adhesion for weaker parts. For these tests, I'm going to be using OrcaSlicer. It isn't my everyday slicer, but when it comes to calibrating filament, its tools are what I reach for. We're going to select our material, in this case ASA, and Orca generates a tower that changes temperature at every step. It has a range of different shapes and details that we are going to compare how temperature affects them. Once it's fully printed, we're not looking for perfection in each one of those details. We're looking for the best overall compromise in one temperature. Starting with overhangs, those ramps all look basically the same on this one, so that's not going to be a deciding factor in this test. On the opposite side, there's a little window with cones in it. That shows us stringing and small detail quality. Stringing on this print improves from 260 Celsius down. The cone quality is pretty inconsistent though, so that's not going to help us much. But we can also stick a screwdriver or a hex wrench in here and snap off that cone. The harder it is to break, the better the layer adhesion is. This is very subjective. You're going to have to feel it for yourself to feel which one is more difficult to break off. And the clearest difference on this whole test for me is the bridging. The bridges at 260 and 255 look best. Hotter than that, they droop more. Colder than that, I can actually see where they're just failing to bridge properly. You may also want to watch your surface finish. Some materials shift between a matte or a glossy texture as the temperature changes. That's not an issue here, but it is something to look for. For me, the best overall compromise between layer adhesion, stringing, bridging was 260 degrees Celsius, so that's what we're going to use moving forward. With temperature chosen, we can start to build out a filament profile. Every test we do from here, we're going to add to this profile, building it out till we're done. While in here, we also want to set our flow ratio to 1. This is going to be the next thing we tune. flow ratio, aka extrusion multiplier. This corrects how much filament the slicer tells the printer to extrude to ensure that we're getting accurate extrusion out the other end. In OrcaSlicer, we're going to the calibration menu and flow ratio. There are only a handful of options in here. YOLO, their recommended, is also the one that I like to go with. I'm leaving right now the top surface pattern at Archimedean chords. I don't particularly like it, but I want to show you what that looks like. This tool generates a handful of coupons at different flow ratios. We're looking for the smoothest, consistent top surface from the ones that are being printed. We need to make sure that there's not too much filament bunched up at the ends, and not gaps in between each of the lines. These are pretty difficult to judge by eye, so I'm happy that I have my overkill microscope. Getting a close look in here, I'm not really seeing what I want to see. Even all the way down at 0.95, the lowest setting from this first pass, we're still a little bit bunched up and no gaps in the lines, so we're going to set 0.95 as our flow ratio and then run a second test. Luckily, OrcaSlicer has this factored in with YOLO Perfectionist. I'm going to set my top surface to monotonic on this one. It's a finer step test that's going to have more coupons. So we're going to now start from our baseline of 0.95 and go up and down from there to really dial in where we want to be. Seeing the gaps in this particular color is proving difficult, so running my fingernail over the lines to feel for spaces between them is proving helpful. Comparing the results, I've gone back and forth and I've landed on 0.93 as the flow ratio that I want for this particular filament, so that's what I'm going to lock into our profile so we can move on to the next thing. For your education, here's a different color filament pushed to the extreme, so it's a little more clear what I'm talking about with gaps between the lines. The next thing we're tuning is pressure advance, and this is one where I think explaining what's happening will help you understand what you should be looking for in your testing. As your print head is moving, pressure is building up inside of a nozzle. But when your print head slows down to, say, turn a 90-degree corner, that pressure doesn't just instantly disappear. Plastic can keep flowing, and that'll create bulged out, enlarged corners. They're not only unsightly, they're knobby knees on your print, but they can also ruin the dimensions that you're trying to produce, making your geometry not correct. Pressure Advance is a tool that helps to anticipate that. It will take the value you provided and reduce the extrusion as the print head slows down, and then ramp it back up as the tool head accelerates. This means that you'll get the crisper corners you're supposed to be getting. If you have too little pressure advance, you'll get the bulges. Too much, and you'll over-thin your corners, if not just totally ruin the extrusion. We're looking for a Goldilocks zone where everything is just right. That knowledge dropped, back into OrcaSlicer we go. Under calibration, we're going to choose pressure advance. I prefer the PA pattern test personally, so that's what we're going to use. I also changed 3 values. PA step I set to 0.00125 for finer increments that'll give us a finer end result. Then speed and acceleration I changed to match the profile that I actually print with most often. Those settings will affect the results of this test, and Orca's defaults may not match your real-world printing. Look at your print profile and set the speed and acceleration you actually use. My profiles prioritize quality over raw speed, so I want to be calibrated for the actual profile that I'm going to be using. Under the microscope, I can show you better what we're looking at. On the lower end, the lower values, we get the bulged out knobby knee. On the upper end, the higher values, we get the way thinned out corners that are just weak. This is all visible to the naked eye, it's just easier to convey in a video under the microscope. We're looking for the Goldilocks result, the point where we've got a good crisp corner, but we're not under extruding and getting gaps in the walls. On this particular test, the result that I'm getting is 0.02825, a really fine PA value. Some folks prefer the tower test, and if my pattern is a little inconclusive, I will run one of these as well just to double check myself. What we want to do with this is again look for the point where things are the sharpest corner, not the bulge, not rounded. We have to measure up from the base to that point, and then take whatever our step value was, if it was the 0.00125, multiply that by the millimeters of height to our crisp point, and that's our PA value. With that variable chosen, we can add it to the profile we're building out and save it so we can move on to our next test, max volumetric flow rate, the variable that can hold back the performance of your machine or unleash the beast if tuned properly. And I do think a lot of folks read this test wrong. I'll talk about what I mean when we get to the results section. For now, we want max flow rate, and then we can adjust our values. I know that the Core One with a 0.4 high flow nozzle will easily go past 20 millimeters cubic, so I'm gonna push my upper end higher up to get the real results. This generates a simple racetrack that speeds up as it climbs up, pushing more and more filament through the nozzle. While that runs, I want to thank Patreon supporters and YouTube members whose names are scrolling by. Their support helps pay for time and materials behind testing like this and keeping the lights on. As an extra thank you, once we're finished, I'm sharing this particular profile and a few other ones with those supporters. I don't normally release these profiles because machines, nozzles, and even batches of filament can vary. Treat these as a reference point, not a magic drop-in settings thing. But if you'd like to get access to the profiles or just want to support Mandic Labs on the whole, please check out the link in the description or the QR code on screen. Alright, let's check those results and see what I mean about people reading it wrong. The point of this test is finding where the hot end can no longer keep up with the requested flow rate. Most folks will look where the first hole appears, stop the print, and measure to there, giving this number. But this whole tower is one extrusion wide, just continually running. That wall is the plastic coming out of a nozzle. As the hot end starts to fall behind, it can't keep up, the wall gets a little thinner. The hole is just where it got so thin and so weak at keeping up that it totally stopped for a split second. What we want to really do is look down this wall for a point where there's a dramatic change in quality. See this line? That's where it began. That's where measuring to this point will get us a totally different number, but the actual thickness we're aiming for. If we really want to get into it, we can snap the layers apart and actually measure the wall thickness at various points, finding the point where it starts to reduce dramatically. How much thinner you accept is your call. I personally want strength and quality from my parts, but speed can be handy at times, so I try to find a really good balance. For me, this test is resulting in 26.6 millimeters cubic flow rate. With that saved to our profile, we're into our home stretch. Our second to last test is retractions. And I'm going to be honest, I skip this pretty often these days. Retractions pull the filament back slightly while the nozzle travels, helping prevent stringing and blobs from oozing out of the nozzle. But if you followed my guide so far and dried your filament, tuned temperature and pressure advance, that really makes up for a lot of what we used to band-aid with retractions back in the day. A modern direct drive toolhead like my excellent neck extruder equipped Core One here really manages filament well. Some finicky materials and high flow hot ends may still need some help, so I'm going to show you how to do this anyway. Back in OrcaSlicer, we head to the retraction test. I'm going to set it from 0 to 1 millimeter in a nice fine 0.05 millimeter step increment. This print is going to jump between those two towers back and forth, retracting before each move so that it strings across there if it's too little and is clean if it's fine, which my result is almost comical. Looking real close, up to the 1 millimeter mark, I've got blobbing, which is the point where there was no retraction at all. So that means mine is 0.05 millimeter where it cleans up. That said, the setting I'm actually going to use in my profile is 0.2. I want a little buffer room in here. 0.2 is not going to be so much that I get gaps in my extrusion from over retracting. It's going to give me some real world room to breathe. With that value chosen, we're on to our final test. Material shrinkage. Plastics contract as they cool after extrusion. That's part of what causes prints to warp and peel away from the bed sometimes. It can also leave your final dimensions of your model smaller than they're supposed to be. OrcaSlicer doesn't have a dedicated test for this, so I made one. Right now, you can get for free on my printables page a 50 and 100 millimeter model that you can print and use the included one-page instruction sheet to calibrate with. We need to import the one we're going to use into the slicer and disable shrinkage compensation. In OrcaSlicer, that means going in and setting the shrinkage value to 100%. Then we just print the model, either at the recommended settings or at the settings you're going to be using for your prints moving forward. And this test is last for a reason. every setting we've already tuned can affect the final geometry, so shrinkage measurements only mean something once the rest of the profile is dialed in. Once this print is finished, we need to let it cool down to room temperature naturally. Then we'll use a set of calipers. A ruler's probably not going to be precise enough for this, to measure X, Y, and Z. What we're looking for is the difference between the intended size and what our actual print size is. We take our readings that we got and plug them into the formulas that are included in the one-page instruction sheet, and that'll give us our shrinkage value to put into our print profile. Once we save it in there, we need to run one more test to confirm our results. An important note on Z compensation, it's pretty frustrating the way it's done currently. Slicers only apply it within layer height increments. A correction smaller than that may do absolutely nothing. Check it, get it as close as you can, but don't pull your hair out over this because it's just not really well compensated right now. And with that, our profile is complete. Now we can answer the question that's been plaguing man for generations. Was all of this tuning worth it? To find out, I'm printing the same two models on the same plate at the same time. A Cali Dragon at 100% scale, and a Voron Cube scaled up to 50 millimeters on all sides. I'm going to be printing these in 3 different profiles, all using the Ambrosia ASA. The tuned profile we just made, Bambu's generic ASA profile from Bambu Studio, and Prusa's generic ABS profile, as they don't have a generic ASA one. The only difference between all of these prints is the filament profile. The actual print profile, speed settings, all of that is identical. And the different colors of all Ambrosia ASA, just so I could easily tell them apart. Honestly, all 3 of the prints turned out better than I expected at the speeds that I pushed. I was not being conservative, and it really got me thinking I could be pushing my Core Ones faster than I do on a regular basis. My profile was the fastest, most dimensionally accurate, and had the cleanest corners and most consistent extrusions. But the difference in overall appearance is minor. The dimensional accuracy is more of an important thing to me. That was definitely the clearest improvement with my profile. And you do have to remember that some things like improved layer adhesion are just not going to appear in a test like this. That said, if you made me pick a generic profile among these tests, I'd pick the Prusa generic ABS one. Yes, Prusa is sponsoring this video. I'm not saying this because of that. I genuinely feel that Prusa's base profiles, filament profiles, are the best in the industry. They have a wide range of not just their materials, but also third-party materials, different types of materials, combinations. I mean, their generic ABS profile, which is just meant for whatever you throw at it, had shrinkage compensation on it. ABS is known to shrink, and nobody really bothers to do that otherwise. Now the billion-dollar question, was all of this tuning worth it? I can't decide for you if this is something you're going to be willing to do moving forward. It seems like a lot in hindsight looking back at the testing, but all of those prints were less than 100 grams of filament used. Yes, that's 100 grams of filament-ish off of your spool that you're not going to have, but you can run this calibration testing once and apply it to that same filament over and over again in the future. Barring any major manufacturing change, which is rare, you should be able to just keep running that profile for years to come. I know that in this video it probably feels like a fair bit of time and materials to get to this point, but think about this. One overnight print, you come in the next day, you look at it, and it's not the quality or strength that you were hoping for. In hindsight, a little bit of tuning in advance probably would have saved you a whole lot of trouble in the end. And I mean, if you just want to sign up for my Patreon and get these profiles, you could do that too. Again, I really recommend them as reference, but they're going to be there. Alright folks, that's going to wrap it up for this one. I hope you found this video interesting. Maybe share it with some friends who are getting into 3D printing and want to get better results. Thank you to Prusa Research for sponsoring this video, and to Patreon patrons and YouTube members for helping keeping the lights on around here, however contrasty my studio is. I hope you folks appreciated and enjoyed this. Drop it a like if you did. Get subscribed to ensure your 3D prints don't fail. It's not a guarantee, but it can't hurt. Alright folks, see ya.